Okay. Uh, so the basically this chapter or this topic this week is multi-phase flow. All right. Uh, Basically, we'll start off with some. We'll only be deal mainly with air, water. All right. Uh, Air water systems. Okay. In this unit, but multi-phase flow can be actually uh, anything. Can be gas, liquid, liquid. Sometimes the two liquids don't dissolve in each other, so they remain as two, like water and oil. Can be gas, solid, liquid, solid, and so on. All right, so it's actually a very broad topic. All right, of multi-phase flow, but in this unit for this we only focus on multi air water systems, and basically I think first there's some the general definitions, notations, etc. All right. Then after that, I think there are two main things. One is we'll do the easy one first. Okay, the easy one is bubble columns. Okay, so that's one basically like your fish tank. You bubble it from the bottom, the bubbles rise. All right, except in your fish, unlike your fish tank, this could be a column of like a pipe. Then the water also can be going up or going down in that pipe. Okay, so in other words, you have a pipe, you have some bubbles here. Bubbles generally go up. Okay, air bubbles generally go up in water. The liquid, liquid can be up here or can also go down. All right, co-current or counter-current flow, bubble columns. Okay, second one is a pressure drop in a pipe. Well, second one, I think they do flow classification. And delta P in a pipe. Okay, this one is mainly pipe flow. Again, normally it's water, air, water, gas, liquid gas system. Alright, that liquid gas system, although we focus on water, air, but like with the pipes or like boiler tubes or condensates or so on, actually the liquid can turn into the gas, the vapor, and the vapor can turn into the liquid and so on. But I think in this unit we don't make it so complicated. Normally you just do water, air. So the air doesn't turn into water, the water doesn't turn into air. But if you have like boiler tubes, you can have water turning into vapor, vapor turning into water, and so on. Okay, so that's what we have in store for you guys. Oh, I have to mention, I see Clayton this time. Maybe they changed lecture. We used to the pressure drop in pipe in the initial few years when we started at multi-phase flow in this unit. They teach the homogeneous flow model. Then after that, they went to a simpler one. All right, more based on experimental correlations and so on. But this year, I see they gone back to homogeneous flow. Okay, so we'll use the homogeneous flow model or whatever they call it. All right. So those who did this unit last year, so this part is different now. Okay. Those who do this unit this year, I'll try to make it as painless as possible. Here, the math is quite involved, and it's in my lecture slides. You can go through it all if you like. Sometimes some people like to eat chili, so by all means go through it. But I'll skip most of it. You just describe I'll just explain it in a more descriptive manner. All right. Okay. So safe. All right. So any questions? Okay. Alright, so that's the plan. Let's see how you. So this set of lecture slides I uploaded. I may have uploaded earlier one, but I changed it back to this one because to keep in line what Clayton is doing this time. Okay. So yes, pressure drop, flow calculation, bubble rise, so on. Alright, so that's it. Multi-phase, normally liquid, with vapor droplets inside. Right, gas droplets inside. Normally, what happens? They'll try the description. Normally, there'll be one continuous phase. All right, so that's the dominant one, and then the other phase is embedded inside. So one's the continuous phase, one's the discrete phase. So depending which what your flow conditions are, what the ratios are, you might get one phase dominating the other one. You can have a gas being the continuous phase and just like a mist of liquid inside, or you can have it on the other extreme. Water is the continuous phase and you have droplets, small droplets of gas inside, depending on your ratios of your mass ratios. Okay. So I think, let's see this one. I'll come back to this one later, flow classification. Whatever. Okay. Okay. So I'll come back to this one. I just want to go through the basic terms, and then we do the easier one first, which is the bubble column. Then only we'll come back to do the flow classification and the pipe flow. Alright? Alright, so notation W M, the capital M is mass flow rate. Alright? Okay. So alright, capital M, mass flow rate. Alright, the subscript G and L is normally this one implies the gas, this one implies the liquid. So mg is mass flow rate of gas, ml is mass flow rate of liquid. Alright, they don't have to move at the same velocity. Right? The liquid can go faster than the gas on average, or the gas can go faster than the liquid. Alright? They don't mix, they don't interact. Now they do interact, but they not necessarily have the same velocity. Okay? So let's keep in mind the velocity may not be the same. Alright? Alright? V of the gas may not normally is V of the liquid. Alright? Not always the case. Not always the case. Alright, like just now I told you the bubble column, the liquid could be going down, the bubbles could be rising up. Alright. Okay, so what's the next one? W. Quality of mass fraction, W. W is normally quality of gas, isn't it? Mg over ml plus mg. Right? So I think in your thermodynamics, all that they call this X, isn't it? Quality. Right? Here they call W, just to confuse you. X. Right? It's the mass ratio. So if X is 0, it's all liquid. If X is 1, it's all gas. That you use in thermo also, isn't it? Alright? Okay. X equals 0, all liquid. X equals 1, all gas. Alright. Okay. M is the total. M is total mass flow rate. Total. Okay. So from here, they can play around like this. Alright? M gas over M is the X, so we expect M liquid over M is 1 minus X. Because X can only go between 0 and 1. Okay? This one, alright, is the void fraction. So it's not the same as X, huh? Alpha is SG over S. S is the area of the pipe. S, total area of pipe or column or whatever is going on inside. SG is the area time average cross section area of gas phase. Alright, so again, if you just take one snapshot, you might think, alright, depending, maybe you get bubbles at equal separate. Alright, in case the flow, alright, you got liquid going here, liquid, and then you got bubbles going through like this. Alright, if you take instantaneous snapshot here, you might say, hey, hang on, S0, all liquid. Is that alright? And then later you take out, you get some number, some value for the, because you slice over here, and so on. Okay? So this S is, if you have an observation point here, and you time average it, and that's your average. Then, because some it will be 0, then sometimes not 0, then sometimes, right? So the time average is that S. Alright? Of the gas phase. Does that make sense? No. Huh? No. Alright, I say again. If you observing here, alright, you can measure the area, no problem, that's the total area. Alright? But you want to find the average area of the gas phase area. Alright? To do that, you need to sample it now. Alright? Not just take one measurement. Because if you take one measurement at this instant in time, you think of SG0. Because you look through all liquid only. Right? Right? At some later time, when this bubble moves here, you get a non-zero value when you slice it. Right? Is that okay? So this SG that we use is the time average cross-section area of the gas phase. Alright? Because if I based on this one here, the area S gas, maybe the instantaneous one. Alright, if I plot versus time, I'll get, alright, every time a gas passes, maybe this is S total. This is S. Alright, S is the total area. Every time a gas bubble passes, alright, or it will detect something. If there's no gas, it might go to 0. If the flow is not so simple, there's sometimes got more gas, sometimes less gas, then this whole thing might be going up and down. Is that okay? Alright? So I need to average that, give you my average gas area. Alright? Average liquid area is one over that. So by right, SG plus SL should be equal to S. Is that okay? Right? If some of you ask how can this be measured, it depends. There are various ways to measure, because the gas and the liquid have different properties you can measure on. So sometimes you can use capacitance, inductance, resistance, or also electrical signals, right? Because the properties of liquid and gas, the electrical properties of liquid and gas is different, so you can use that. A lot of ways to do that way. Sometimes you can do optical way, right? You have to take snapshots and then measure. Or sometimes you can do ultrasound and so on. So there are a lot of different techniques to measure, right? This thing, if you need to measure that now. Okay, but no, luckily we don't need to measure that in this unit, but it can be measured now. Okay. Okay, and is that okay? So far our definition, all the simple one, mg, omega, alpha. Okay, anything? M is the total mass, S is the total area. And we break that up. Anything else? Alright, what is G? Yeah? G is the mass flux. Alright. G is the kilograms per meter square per second. Alright. So the m dot per unit area. Alright. That's G. Okay. My notes here. So G is m over s. Alright. So as the units of kilogram per meter square per second. The flux. Alright. M is GS. mg. Again, this is the mass of the gas. Is the mass fraction multiplied by GS. G is the mass flux times area. It's actually how much. Right? It's just other way of writing it. Well, normally we use the small v, isn't it? Yeah, I think they use the big V. Never mind. All right. Big V is the specific volume. So V of the gas is the specific volume of gas. V of the liquid is the specific volume of the liquid. Okay. All right. Let's. I think this one. No, don't touch it on first. This one. mg. All right. Mass of the gas is rho times velocity times area. The area is alpha times s. Alpha is the void fraction. Is that so? What this one says, all right, this is just rho VA. But for the gas phase, it does not use the whole area. It only uses alpha times S. All right, alpha times S is the what S script G. All right, and rho G you can put as 1 over VG. All right, so you can express UG in terms of mg VG over alpha S, or mg can be expressed as this one times this. This over this is actually G. Mg is actually omega GS. So S, the top S here will cancel with the bottom S and you get this expression. Is that alright? For the liquid, it's the same, except here alpha is alpha minus 1. Okay? This is the wrong way around, isn't it? This should be 1 minus alpha, sorry. Alpha minus 1 is negative value. This should be 1 minus alpha, and here also should be 1 minus alpha. Typo it. But here I got it correct back again. Alright? Okay. I think that's all we need for the terminology. Okay. Okay. So U is the velocity of the gas, and U subscript G is the velocity of the gas. U subscript L is the velocity of the liquid. Alright? And as I said, they don't have to be the same. The gas can be, on average, moving faster than the liquid, or the liquid can be moving faster than the gas, or they can even be moving in opposite directions. You all okay with this? You all happy? Yeah. Okay, so as I said, this part is all the pipe flow one. I skip ahead first. So just sum up here. U, I think what mg is rho of the gas, U of the gas, alpha S is the area of the gas. So is equal to UG alpha S over M over VG. Okay. So UG is equal to mg VG over alpha S. Mg is what? WGS. Right? WGS VG over alpha S. Cancel out. Is W G VG over alpha. UL, I guess you can show the same. This will be 1 minus omega GVL over 1 minus alpha. Is that right? Yeah. Okay. UL, you could do the same thing, but everywhere where omega appears is actually 1 minus omega, where this one is 1 minus alpha. Okay. Okay. I'll come back to all this painful part here later. Okay. As I said, we do the easy one first. We do bubble column first. Okay. Right. So what I plan to do with this bubble column, I talked about it. I show you how to do it. Then we do the tutorial problem. Right. This lecture and tutorial combined. Alright. And then after that, maybe we take a short break, and then come back and do the hard part, the pressure drop, flow classification and pressure drop. Alright? So, okay, so this one bubble column. So used in many reactors, bioreactors. Positive channel is defined as upwards. Alright, so sparging is actually just bubbling. Alright? Pump the gas at the bottom and let it go up the top. You can also pump the liquid so that you have cold current flow, or you can pump the liquid downwards. In other words, take the extra liquid up here and put it on the top, and you get counter current flow. A lot of times, this one used for in the bio area and in the chemical processing area, because maybe you want some reaction to happen normally. Alright? So you want maybe some reaction happening, maybe the gas is you're producing the gas, or using the gas as a catalyst, or using the air just to do some gentle mixing or whatever. So that's the application. I'm sure there are a lot of applications. Right? Sometimes the gas, the air used to collect, used to trap oil or whatever. So you want to do oil liquid separation. Sometimes it's yeah. Sometimes you want gentle mixing, so you pump gas instead of using a mechanical agitator. Okay, so same thing again. Here Q, what's Q? Q is the flow rate. All right, Q is Q is flow rate. M over S. Right. Okay. My slide's a bit out of order. Okay, so I should actually talk about one bubble first. Okay. So some furnace, it's not so easy to predict theoretically. So some fellas have observed and studied how bubbles rise in columns. Alright? So you study one bubble first. Alright? Watch one bubble. You ever watch one bubbles rising up? Alright? Okay? So, let me explain a little bit. Okay? So if this is your surface, we'll start with one bubble first, then later we do more bubbles. Right? One bubble. Okay, so your one bubble. You think, when the bubble rises, you think it stays a sphere? No, right? Okay, that's why the sphere thing is not so suitable. Okay, because you cannot just assume that they are spheres. What happens is they tend to be, especially if they're big, they tend to be, as they rise, they tend to deform. Okay, because you have the fluid flow. All right, it has its own mg, which should be quite small anyway, because it's gas. It has its F buoyancy, so it's rising, and the flow is so it has some drag. Okay, due to the flow. So these are the forces, and not number one. Okay, so it's obviously not a sphere, so that complicates matters, especially if it gets bigger. If it's very small, then maybe it's very spherical. But big bubbles, then no. So you watch that. They go to swimming pool and grow bubbles. Alright? And the other thing is, inside here is not solid. It's a vapor. It's a gas. So it tends to circulate also. Right? This circulation of air inside the bubble tends to assist them in rising up, make it easier. So the drag is not so high. Because if you are solid, here will be a wall, you have boundary layer and all that kind of things. But this is not a wall, this is just an interface. The air inside here will recirculate, and that will help the bubble rise. Okay? So the bubble will typically rise, or velocity is typically will be much larger than if it was a solid. Okay? Definitely larger than faster than rising a solid ball, and definitely even if you deform ball, it will still be larger because the internal circulation inside overall reduces drag. Right? Internal circulation reduces drag. Okay. All right. So let's go back here. Is this all okay? Any questions? So this is just an overview of what's the physics. All right. This is, I think, in words. Right. So the internal circulation can help it up to 50% increase. Contamination interface between gas and liquid can reduce thermal loss expression of small bubbles. This one, the bubble interface. The bubble interface, there's surface tension there. Alright, and surface tension can be, even the smallest, slightest amount of contamination or what will change the value of the surface tension. So that's just so sometimes what you predict and what actually happens is quite different. So surface tension very sensitive. Even the slightest amount of oil or other contaminants, surfactants, whatever inside your thing, you cannot. It won't behave like distilled water and air anymore. Alright. Okay, so what we have, Alright. So these ones are correlations. So it's determined experimentally. Can you see it? Huh? Okay. Is it better if I... can you see? I think there's color missing, eh? Yeah. maybe I get from their one. I think there's a color missing, isn't it? Like just like non-Newtonian. Two-phase flow. I think this will be lecture 1. Okay. My ordering a bit different than theirs. Those 3 slides are available on your Moodle. All right, my ordering a bit different than theirs because I believe my ordering is a bit more logical. Okay. Okay. All right. So I think this is the table I wanted to show. Okay. So the bubble rise velocity of a single bubble depends on many factors. All right. Mainly the Reynolds number of the bubble. All right. And what is G1? Morton number. All right. So they incorporate all the main forces at play, viscous forces, the drag. All right. And Morton number, I think, is the surface tension effects. All right. So I think these ones are low Reynolds number. These are for very small bubbles. Okay. This some correlation they can use to predict the velocity rise. And down here is for very big bubbles. All right. What is the Reynolds number for the bubble? Reynolds number for the bubble is the raw liquid velocity, terminal velocity of the bubble, times 2 Reynolds number of the bubble divided by mu viscosity of liquid. But UT you don't know. You guys very good at guessing already, isn't it? Right? So you need to guess what that velocity is first, and then put in here, and then if your guess velocity is actually the velocity you find, then it's correct. But here you got so many to look up. I think this one, we hardly ever use this one. Okay. Alright, and Morton number, there the G is the gravity, mu L is the viscosity of the liquid, and P sigma is the important rho L density of the liquid. Rho is the Morton number. Sorry, the surface tension. So the two things that are important at play here is the viscosity, is the viscous effects, the Reynolds number, the drag, and the surface tension. Right? That's the surface tension between the liquid and the paper. Right? Well, got G2 also. Here got G2. Right? G2 add more parameters inside. I think also some combination of the Reynolds number and the surface tension. Alright. So basically, I think to sum it up, the top one is for small bubbles. If you expect your bubbles to be big bubbles, then it's the most likely they're down here. Okay? I think in most cases, big bubbles are. Alright. Okay. So this one, don't worry, you don't need to memorize the formula to be provided. Okay, there's G1, and even for larger bubbles, all right. Instead of using this one, I think there's an improved version here. Okay. All right. So this we'll check whether I don't think they need, but this one is for we'll have a look at the problem whether required to use or not. I don't think need. Okay. It's just here in case you do need to calculate, but I think most of the time they do give you the velocity of the bubble right here. Alright? Not you need to calculate this one, which is complicated because you need to guess the bubble velocity before you can work it out. The next part here, this last section, is actually I haven't gone through the flow classification, but this is actually called slug flow. Just now was bubble in a very big tank. Alright? So if you in the case where you have slug flow, which is bubble constrained in a tube, a pipe, okay, that's like a slug, a piece, a continuous big chunk of piece called a slug. Alright? So if you have slug flow, then the bubble rise velocity is a bit different. Alright? From potential flow theory, you get the bubble rise velocity there. That one is quite different case, specialized case. Alright? Large bubble constrained by the wall and so forth. Alright? I'll skip this part. Alright? This one, this description here is to aid with the, what do you call it? Is to aid with the calculation of bubble rise velocity for continuous system. This was single bubble, all right, and this one for continuous system. Also got more numbers. All right, JG and JL is the basically the velocities, right? Because it's QS over S. Okay? No, it's QS, the volumetric flow rate over the area of the pipe, and the volumetric flow rate over the liquid over the area of the pipe. K1 comes from determined experimentally, comes from the graph next door. G and dP is what? Diameter of the pipe. Right? So K1 you have to look up, and it's dependent on these numbers here. Okay, that's K1. And it's dependent on these two numbers, this one and that one I can't see also. Which I think here. Alright? This is one of the dimensionless numbers, and I think G1. These are two dimensional numbers. Okay? It's just applying experimental correlation. Alright, if you need to use I don't think so. You'll see the tutorial problem later. Okay? If you need to use, we'll look it up. Alright? I don't think so. Alright. So basically there's three things here we covered. Alright. Bubble rise velocity for single bubble in a big tank. Rise velocity of a single slug in a pipe, and bubble rise velocity for a continuous system. Continuous slugging system means not only one slug, but slug after slug. Then it's this one. Okay? Which we need if we apply these experimental correlations too. Okay? Any questions so far? Alright. So let's to put into practice. Okay, here. In reality, we don't have one bubble. So that's where we go here. No, it's gone off now. Okay, in reality, is this one. Alright? So, when you have a lot of bubbles, alright, the bubble, okay, so ut is the velocity for a single bubble rising. Alright? When you have multiple bubbles, when you have a system with a lot of bubbles, the velocity actually slows down. And it slows down by this factor here. 1 minus alpha to the power n minus 1. That's the Richardson-Zaki equation, fits most cases. Alright? Alpha, what is alpha again? Alpha is the void fraction, isn't it? Okay? So, if the void fraction is close to 0, right, means, sorry, void fraction close to 0 means what? all liquid, isn't it? Alright? Void fraction goes to 0, 1 minus 0, 1. 1 to the power anything, 1. You get this one. Cannot. So as your void fraction increases, then this factor will be less than 1. Alright? And less than 1 to the power of something will be even smaller, so it will reduce the terminal velocity. Okay? It's like traffic jam. Right? In one bubble, it will rise faster, but once they're rising on multiple bubbles, it will slow down. Is that okay? So n is some constant depending on the Reynolds number and so on. Alright? I think in most equations they'll tell you that what that n is. Okay? So typical values of n. Alright, for very small Reynolds number, n is very large. For larger Reynolds number, n is normally around 2.4. Okay? Again, this is based on experimental observation. Okay? Okay. Now, previously we had we were just considering the stationary liquid and a bubble rising, and then we call it UT. Alright? But actually, alright, okay. So big tank, so small bubble in a big tank rising, and we call that UT, the terminal velocity of the bubble. Alright? Now that there are many bubbles, okay, so because they interfere with each other, they block each other's path and so on. So UT, so this bubble rise is UT 1 minus alpha to the power n minus 1. Okay. This is actually, if let's say the gas, this is actually the difference in velocity between the liquid and the gas. So this direction positive upwards. Alright, so in other words, U gas minus U liquid is equal to UT 1 minus alpha to the power n minus 1. Is that right? Did I copy correctly? Okay, yeah, I copied correctly. Alright. Okay, so far. Alright? If the liquid was stationary, then that's fine, that's just the velocity of the gas. Alright? But the liquid can be moving also. So if the liquid is moving downwards, then you expect the gas velocity to actually be lower. Alright? These are all absolute values. Okay? So it's, in other words, this is actually the difference in velocity between the gas and the liquid. This is the bubble rise velocity. Alright? If the liquid is flowing upwards, then you expect the bubble to rise even faster. If the liquid is flowing downwards, you expect the bubbles to actually rise slower. Alright? Does that make sense? And this captured here, U gas minus U liquid is equal to this one. Okay. Let's follow carefully. Okay. So U gas is, let's see here. U gas is the volumetric flow rate of gas divided by the area of gas minus the volumetric flow rate of the liquid over the area of the liquid. 1 minus alpha S. All agreeable so far? Okay. What we intend to get here, all right? Normally, we would be provided with either the volumetric flow rate or mass flow rate. We want to find the void fraction. Normally, that's the problem. Okay, that's the normal problem. I don't think this one you'll go backwards. Give you void fraction as you go there. Okay, so normally no. So we normally want to find the void fraction. So we want to repackage this equation nicely to form, and let's see how we repackage it so that we can solve for the void fraction. Okay. So here. All right. Okay. Yes, I equated that. So multiply by 1 minus lambda on both sides. So let's do that. Okay, let's say what the thing asks us to. So here it will be QG 1 minus QL over S is equal to UT 1 minus alpha. Since we multiply 1 minus alpha to the n only. Okay? Then after that, do what? Alright. Hey, how come they get alpha? Oh, sorry. Multiply by alpha 1 minus alpha on both sides. Multiply by alpha 1 minus alpha on both sides. So this one, we get 1 minus alpha. So yeah, correct. This one should get alpha. And here you get this one minus 1 and here alpha. Is that alright so far? So multiply both sides with alpha 1 minus alpha. Please, give me somewhere. Then what do we do next? Can't remember. Okay. Alright, this term here is actually called the, what it says here? This is the drift flux. UGL, drift flux. Right? Is mass flux is the volumetric flow rate per unit area of bubble. Okay. Come on, I'll skip this one. Right? Okay. Let's see. What are we intending here? Alright. I think this is what we want already. Okay. Actually, this is what we'll use already. So I'll put this in box. Okay. Okay. But the lecture slides actually talk a little bit more here on what is drift flux. All right. So take a note. We'll actually use this equation here. All right. If you solve this equation here, we can find alpha, but it's a bit difficult to solve. Like there's alpha here, there's alpha here, there's alpha here, there's power n, and so on. Okay. Yeah. Okay. So leave this aside, but when we come to doing our problems, we'll be using this one. This one, since I mentioned what drift flux is, I think this extra slide here is just to tell you what drift flux is. It is actually this one, QG S. Alright, so you can UGL, which is essentially the left side of what that equation I showed you, can be rearranged to write in terms of QG over S minus that one. Is that okay? So I think from here to here, this QG over S is here, minus alpha, move to this side. So it's minus QG plus QL over S, alpha. QG plus QL, that's the total Q. Q over S So it's actually Qg over S multiplied by Q over S. Alright? So this is actually, that's why they call it the radial flux. This is the average velocity of the gas minus the average velocity of the entire system. That's what UGL means. Okay? That's why they call it radial flux. Therefore, UGL is the velocity of the gas relative to the entire system multiplied by the volume fraction of the gas. Okay. Alright. So, yeah. But as I said, this is extra. Normally, as I said, we want to find, we will normally be given either mass or volumetric flow rate of the gas, of the liquid, alright, terminal velocity, normally given. What you need to find is alpha. So looking at this, a bit hard to solve, isn't it? Alpha appears here, 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 and here. Why not? You can guess, alright, if you like, you can guess the value alpha, put in here, work out this value, see whether the equate or not. If the guess is correct, you'll equate. Alright? But that is not a systematic way of doing it now. Alright, a systematic way of doing it is you can plot a graph. This one is actually a straight line. Okay? So, where my notes? Okay? Yeah. Alright, we want to solve this equation. Normally you can plot this here, you plot alpha. Okay? Left hand side. Okay? It could go negative, alright? But this is essentially when alpha is 0, this is just Qg over S. Is that right? When alpha is 1, this value here, it could be positive or negative. Let's just consider positive for now. Alright? QL over S. So it's a straight line, isn't it? There's no, it's just a linear line. Alright? When Q alpha is 1, here 1 minus 1, 0, you just get a 1. And anywhere in between, if you try to plot, you actually get a straight line. Alright? Okay? This other one, alright, when alpha is 0, it will be 0. Where alpha is 1, it will be 1. Because 1 minus 1, also 0. So it's going to be like this from here to here. Alright? So if you plot this is the left hand side. This is the right hand side. If you plot, you get something like this formally. Okay? This is if you vary alpha between 0 and 1 and put down the values, you get something like this. Alright? So in this case, you will have two solutions. Solution A and solution B. A is basically alpha void fraction small. Alright? Alright? Remember I told you there's two possibilities. You could well, no, I didn't tell you yet. Well, there's two possibilities here in the case when you get two solutions. When you have here is less bubbles moving fast, because remember the flow rate is fixed, all right, for the gas, and liquid the flow rates are fixed. So you can have two solutions. Solution A is small bubbles moving fast, all right. So there's less, not smaller, but less bubbles moving fast. There's less slowing down of the bubbles. That's why it's a smaller void fraction. Solution A is less bubbles, less bubbles, moving fast. B is more bubbles, moving slowly. Alright, so I told you when there are more bubbles, they tend to cause a traffic jam, they tend to slow down. Alright? When there are less bubbles, there are they tend to move faster. To give you the same mass flow rate of gas, you could have either less bubbles moving faster or more bubbles moving slower. Alright? So this particular system can actually have two solutions. Alright? And both solutions will satisfy the gas flow rate and the liquid flow rate. Alright? That is provided. Okay. Is that right? Okay. Right? Because as I said earlier, more bubbles will be moving slowly. Is that okay? Right? So now I see some people a bit sleepy. So we'll do the problem now. We got enough. We've done enough theory here to do some problems. Alright. Shall we? Okay. So before we do the problems, just some typical solutions are. This one is not this one is too idealistic. When you actually plot it, you won't get a symmetric dome like this, or you'll get a more funny shaped one, right? It's more skewed one side because of the power of n. So, alright. So some problems. Okay. Alright. So Q gas is normally positive. Alright. If you have co-current flow, in other words, the liquid is also flowing upwards, your QL will be positive. But in this case, QL is negative or minus here, is because it's counter current flow. The liquid is flowing downwards, the bubble is rising up. Okay. That's why it's a negative here. In this case, not all cases you have two solutions. Some cases you only have one solution. That's the solution. That's the void fraction for that particular system. Alright? The average, time average, what's void fraction again? Time average area that the gas occupies. The time average cross-sectional area that the gas occupies. Alright? In some cases, alright, you might, okay? Alright, what's happening here? If we reduce the liquid flow rate, the void fraction increases. Right? Reducing means liquid flow rate. Means actually reducing in this case, increasing the downward flow direction. We expect the intersect to go down. We reduce the liquid flow rate. Alright? In other words, the bubbles are rising slowly, so the bubbles are rising faster to meet the actual flow rate. Okay. Hey, I might be talking the wrong way around. Hey, sorry, I've been talking. I made a mistake. Here is QL A1. Hey. Sorry, I made a mistake. So if QS is 1, so if alpha is 0, this is QG over S. If alpha is 1, here 1 minus 1, 0. 1 minus 1, QL over S. So sorry, this position, this value here needs to be minus QL over S. Alright? Okay. Alright. Alright. So in this case, sorry, my mistake. Correct. This is actually, no, it says up there, co-current flow. I thought it was something else. Co-current flow. QG is positive, QL also positive. But because here we plot minus QL over S. So this is co-current flow, one solution, that's fine. if we increase the co-current flow, okay, alright, co-current flow, and we increase the liquid flow rate, so the liquid is also flowing in the same direction as the bubbles. Alright, we expect we use the liquid flow rate. We use the liquid flow rate, so it's reducing, it's going this way. Alright, the void fraction increases. Okay, and finally, that's why not this one wouldn't make sense. This one is the counter current flow. Alright, counter current flow means the QL is negative, so the QL is going downwards. Alright, bubbles are rising, the liquid is going downwards, and you minus that. Alright, and so QL is negative, minus, that's why you get a positive value. Alright, that's when you can possibly get two solutions, and possibly you can get up to no solution. Alright, the no solution case, the top one, is if for counter current flow, your liquid can flow so fast down there, so fast downwards, that it stops the bubbles from rising. Alright, and I think that they call that flooding. So the last solution up here, this one, no solution, never intersects. Alright, so that is flooding. Alright, bubbles will coalesce and form bigger bubbles, right, and rise, or they'll try to. Alright. Okay. Okay, so what will happen in reality is, no, you may not get all your liquid, your bubbles accumulated down there. What will happen is, because UT is only for a specific size of bubbles. If the bubble gets bigger, normally the rise velocity is higher. It will coalesce, form big bubbles, and try to push its way up. Okay. Okay, I think now we can do the solution. All right. Save. Cancel. Is there a problem here? No. Let's do the tutorial one. Okay, save this one. Can I download it? No. You can download it, go here. Login. Okay, we'll do the same tutorial problems as in Clayton, so that should prepare you, hopefully, at the same. Okay, what's that one? Two-phase flow. Okay, I think you can do question 1 and 3 already. Question 2 and 4 is the pressure drop one. Question 1 is all right. So you do question 1 first. Here. What's this one? What's this one? Yes. Tools, select and zoom. Okay. So what's our equation? Q G over S, 1 minus alpha, minus alpha, QL over S equals UT alpha 1 minus alpha to the n. Okay. So in this case, for part A, QG over S is 0.06, QL over S is 0.06. Straight line. Alright. So that one is co-current flow. Positive is upward direction. Positive is upwards. Alright. So both the gas is moving upwards and the liquid is also moving upwards. Alright. UT is 2. No, sorry. N is 2. UT is 0.5 in this particular case. Alright. So actually the only unknown here is alpha. You can try to figure it out, but let's do the way that the notes. All right, so I draw small here, you draw to scale. Right? Maybe 1 cm. I recommend a 1 cm, maybe equals to 0.01 or something like that in the vertical. In the horizontal, maybe you need to go from 0 to 1. How wide your page? Got 10 cm. Maybe 1 cm, 0.1 or something like that. 10 cm, 4 inches. Can, okay, that's your scale. This is your Y scale. This is your X scale. Okay, so here in this case you have 0.06. This is QG over S. Here you have minus 0.06. This is your QL over S. Minus QL over S equals to minus 0.06. You'll have a line like that here. Alpha equals to 1. Alpha equals to 0. Alright. Then next step, you put in later on, once you get a better hang, you maybe don't need to do so fine intervals, but just calculate this value for at 0.01, at 0.02, at 0.03, at 0.04, dot 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 up to 1. No, not so fine. There you go, 100. Sorry. 0.1, 2, 3, 4, up to 1. Okay? So you need to calculate 8 values. Because the first value is 0 and the last value is 0. You need to calculate from 1 to 9. Is that okay? It's obvious, 0, 0. Okay? So, and then after that, you have it won't be like this. I think it'll normally look something like this. Okay? And then we find the intersect. That would be the answer for question 1. Part A. For those who didn't read the question, I'll push it up a little bit. So part A, I think you have 1 solution, I believe. Part B, you have 2 solutions. Part C, you're supposed to move the line up and then find when starting to start to occur. Yeah? As I told you, you put 0.1 in here, UT, which is 0.5 times 0.1 times 1 minus 0.1 to the power of 2. Go back, answer that, right? So there, that's 1. Right? You put 0.2, put inside here again, you get another answer. Put 0.3. Alright? You need to do that 8 times. If you're lazy to do it 8 times, Maybe you do 4 times, you ask the person next to you do 4 times. You do 1, 3, 5, 7, the person next to you do 2, 4, 6, 8. Right? Because later you realize, I think all the intersects are near the bottom here one. So maybe no. Maybe do final here and quarter here and so on. That kind of thing. Pause the recording a minute first. Alright. For part B, QL over S equal to minus 0.06. So for part B, your answer, your problem, the curve is still the same, but here 0.06, here also minus QL over S equals to minus equals to minus of 0.06 is equal to 0.06. You have a straight line, right, for two intersects. For part C, you rise it until there's no solution. Find that QL over S. Okay. Any questions, queries, or anything? So that's a warm-up question. Let's should I start question 3 now, or okay? All right. I start question 3 now. If you still need to work on this, after question 3, we'll take a short break. Maybe you need to eat something, or I hope none of you smoke, but if you have to smoke, right? I hope you don't. I don't endorse that practice. Okay. Where's question 3? Okay. Bubble current with co-current flow. Alright, means the bubble is rising. Alright, and the liquid is also moving up. Co-current. Alright. The terminal rise velocity independent of diameter. So first, I think you need to, they're implying you have to find your UT. Okay. So where is it? That one you cannot see, so I have to go here. Okay. So before that, the bubbles are sufficiently large such that the terminal rise velocity is independent of their diameter. So in this table, no, not this table. In this table, the diameter is, this R is the radius of the bubble. RPE is the radius of the bubble. Alright? So if you, basically I told you the top one line is for small bubbles and progressively bigger bubbles. Alright? You notice of these four equations, which one does not have a bubble diameter or bubble radius inside? Last one. So you use last one. Okay. So small bubbles, moderate size, and big bubbles. So here the estimate is ut is 1.18 g sigma over rho L 0.25. So we need to use that one. Not bad, huh? G. Okay, so that is equal to minus, not minus, is equal 1.18, G is 9.81, what is this, water is it? And water, so raw liquid is water, 1000 or 998 to the power of 0.25. What is sigma? Sigma is the surface tension of water and air. There's a machine to measure it. It's called a goinometer. I don't know where I can type. I think it's called goinometer. Let's see this. No. Alright. Actually, yeah, correct lah. There's a machine in the chemical engineering lab on level 5 that measures the surface tension of. You can measure surface tension on anything, water, air, and so on. Alright. It does that by measuring the contact angle. Okay, I'm deviating off the point here a little bit. Okay, alright. So you got textbook, anybody? Nobody got textbook? Look on internet. Surface tension, water, air. So when you measure surface tension, the other thing is very important. Let's say like you drop a droplet on the table, all right? Then the table surface, the water, and the air all plays a role. There's a three-phase thing going on there to measure the surface tension. All right, but in this case, it's just water and air. So what's the number? It's normally very small, and the unit is Newton per meter or foot per pound per foot. And a slight variation with temperature. What temperature? You say. You prefer 20 or 30 degrees? 20 degrees. 7.28 times 10 to the power minus 2 Newton per meter. Alright? I think your textbook also, right? So this is the surface tension between air and water. Alright? If you change the gas, you change the liquid, you get a different surface tension value. Actually, there was a surface tension here in this unit. I skipped, because I saw Clayton also skip. All right. Okay. So that maybe 7.2 times 10 to the minus 2. What number you get? Surface tension. This force is force per unit length. So basically, if this was the water surface, right? This is the surface of the water, and you put your block here of maybe. Oh, never mind. Let's just change this. All right. If this was the water surface, and maybe this is maybe a piston or whatever, okay, F, the surface tension is this force here. This force, surface sigma times L. Alright? L, where L is the perimeter. Okay? So that's why the sigma has a units of force per unit length, because the surface tension is this. These two are equal. So the force pressing down on that piston must be matched with the sigma times L. Sigma is the surface tension, L is the length, is the perimeter of this block. Because the surface tension doesn't act here, but acts only at the perimeter. Right? So if this block doesn't penetrate the water, that is what is sigma. Actually, F equal to sigma L. This force is at a particular angle, say theta. So sine theta. Okay? Because we need to match the only the vertical direction. Right? So that is what surface tension is. If the tension is, it holds the surface together, alright, and to penetrate that surface, you need that force to overcome this surface tension. Okay, that's a sign. That's what surface tension is. What's the number answer here? Huh? Hopefully, I get a sensible value. Huh? What's the answer? What's the answer? 0.19. Okay, bubbles rise quite slowly. Okay. Where's the question? Alright, independent diameter. The internal diameter of and height of the column is 5 cm. So the column here is 5 cm, and here is 50 cm. Okay, so here I think you can go S. S equals to pi 0.05 squared over 4, pi d squared on 4. Alright, in meter squared. Okay. QG is this one. QL is that one. QG equals to 0.12 times 10 to minus 3. QL is 0.12 times 10 to the minus 3. So I think you can find QG over S is what? Therefore, QL over S is what? Alright. Then the next step would be this is already A. The slip velocity is this one. This is the answer for A. Okay. So part B, I guess we need to find alpha first before we can do that one. Part B. No need what? They tell you alpha here. Never mind. So don't need lah. Don't need to find lah. Okay. UGL, volumetric flux of the bubbles relative to a plane moving at the volumetric average velocity. I think it's Q G minus Q total over S multiplied by alpha. Is that correct? Yeah. Huh? Yeah. So yeah, sorry, no. Part A not finished yet, huh? Slip velocity is actually this one. Sorry. So part A, this is UT, what do you call that? US. U slip velocity. This one, the mistake is, so I thought they you needed to calculate alpha, but since they give you alpha, so life is quite easy. You don't need to do that plot now. So U slip velocity UT 1 minus alpha to the n minus 1. What is n? Okay. I believe you can choose n from here. Alright. Take the, here looks like the Reynolds number is not small, it's moderate size to large, so can take n is 2.4. Alright. Here n equals 2.4 large RE. Okay. Alright. Yeah, of course. Sorry, my mistake. I automatically assumed we needed to find alpha before we could find all these things. But since they give you alpha, so alpha is given, so you don't need to do the plot. So you can straight away find slip velocity. You can also find this one. Alright. This is the UGL. Velocity of the gas. Velocity flux of the gas minus the average velocity of the whole system. What's this answer here? 0.13. 131. What's the answer here? Q total, you add both, huh? So on Q total. I think this answer should be in meters. ABC What's the answer? What's the answer? What's the answer? Zero point 037 317. So, if you are still confused about this one basically, you look at it, this is the volumetric flow rate divided by the area of the bubble. So, this is actually the velocity of the bubble. Alright? This is the velocity of the whole system, average velocity of the whole system. So, this QGL is basically the velocity of the bubble minus the velocity of the system, average velocity. So it's the drift velocity, how fast the bubbles are drifting as opposed to that. How much faster the bubbles are relative to the average flow. Okay so far? Alright. So the final, okay, any more questions? Alright. So the pressure drop both for bubble column, alright, okay. For bubble column, the pressure drop is normally just rho GH, alright. So G no problem, H no problem, is that okay now? Alright. Rho has a slight problem, which flow to use, air or water. Alright. So we use the average by volume. So the volumetric average is alpha times, alpha is what? The void fraction is the fraction of liquid gas, isn't it? Rho G plus 1 minus alpha rho liquid. Alright. I did air, so I think I can just use 1.23 normal atmospheric pressure. Here 998. Alright. So this is the volume average density. Alright. Because alpha is based on volume and not based on mass flow rate, based on volume. So this is the volume average density of rho gauge. This volume averaged. Okay. What's the answer? All right. What time should we resume? Uh, 12 o'clock or 1 o'clock? Huh? 1:30. Huh? 12 o'clock. Okay, we resume at 12 o'clock. What's the answer? Huh? 0.3.72. 3.72 kPa. Okay. Then we will resume at 12 o'clock. Enough time. You should eat something. But don't eat too much after you finish eating. 12 o'clock. You want a bit more time? It's okay. 12:15. If you give you too much time, then you go far away. Then you come back late. So don't go too far away. But 12:15, huh? Yeah, pause this one. Okay. The second half. Hopefully it's shorter than half. I think. Looks like half. Alright. The second half. There's two parts we are looking at. Firstly, flow classification. Alright. So this second half is all about flowing gas and liquid in pipes. Alright. So just now the other one is a bubble column. It's a bit different, huh? Bubble column is more like a reactor. Normally the flow is normally they are vertical. Alright. Right? Normally they are vertical and they are used for the reaction or for something to happen inside. This one is more for fluid transport. This one is pipe. Huh? Okay. So for fluid pipe, for fluid transport, so that's why I separate them. Normally both the gas and the liquid are flowing in the same direction. Huh? They don't go counter each other. Alright. So I think in vertical one picture, depending the ratio how much gas and how much liquid you have. Alright, if you have mainly liquid with a little bit of gas, then it's in this one. As you increase more gas, you get this one. Alright, so the gas starts to form big slugs. Increase more gas, it starts to churn flow. Alright, so this one, the slugs start to become unstable, higher velocity and so on. And then even more gas, they start to have the central core becomes more or less gas with a bit of I think here it's also this and also a bit of small droplets of liquid in the middle. And at very high gas flow rates, it's essentially gas with a bit of liquid on the side. The reason why the liquid sticks on the side is because the liquid has a higher surface tension, right? So it tends to stick to the surface rather than inside. Okay, so from very little gas, a lot of liquid to very little liquid and a lot of gas. Right, so the flow regimes change. Later on, we use the homogeneous flow model. They're actually meant for sort of this region here, the central region. Right. Okay, so there's description here you can read. All right, from gentle bubbles to churn to wisp to this side gets very more chaotic. Alright, so this one was vertical, this one horizontal, also you can see the same picture, except horizontal gas is lighter, so they tend to go up, liquid go down. So from bubbly flow, little bit of bubbles, to more bubbles, become slugs, to stratified like this, and then after that it becomes, the gas flow rate increases, it starts to form waves on the surface. Waves get so big they actually touch the ceiling of the pipe. And then for the last two here, where there's very little liquid and a lot of gas. Right, so the different flow regimes here. Okay, and also another description. If you have to, there are few ways to classify the flow, few methods. All right, this is one method. For some reason, there's no tutorial question here for this problem. But if there was a problem, basically what you need to do is calculate using this. If you are provided this map, I think this map or name also. I think you look in the notes. Name after the people that charted this out. Alright, so they did a lot of experiments and then they figured out where the boundaries are. So rho liquid squared multiplied by J liquid. J liquid is the Q liquid over S. So that one we know here. Alright, so you calculate this number, then you know where you are here. You calculate that number, rho gas squared times JG, J subscript G is that one. Then you know what number you're there. Then if you're, let's say, here and here, then you go right here and then you see, okay, I'm in this region, slug flow. Is that clear? It's normally quite easy. Normally there's a practice question, but this time there isn't. Alright? But this is only one way. There are other ways of classifying it. Alright? No, other people have also written and charted out using slightly different method. Okay? But I think this is all you need to know. Okay? Alright. So, just a note, in some cases, let's say, this one I think boiler tubes. Boiler tubes initially coming all liquid. Alright, then as it starts boiling, get a little bit of gas. As more boiling, get more gas, and more gas, after all gas. So actually the flow will go through the whole spectrum, from liquid to bubbly to all the way up to the water. It's all virtually all gas, all water vapor. Okay? So you could have a situation like that. In reality, but in this unit we won't study so complicated now. Alright? Here. Okay. So that's it for flow classification. It's pretty short. Some still back, not back yet. Alright. Now this one, the difficult part. Alright, as I said, I won't go through in detail all the equations. I tried going through it a few years ago. I don't think many people understood anything anyway. So let's just, I go through just the overview. I don't go through each equation by equation. But if you want to, by all means. Okay? For flow in a pipe, there are three basic forces acting. Alright? The first force, alright, so this force, this is for these three in total will contribute to your pressure drop. The first one is friction, alright, wall friction, shear stress on the wall, alright, that you all know already. The second one is gravity, alright, so elevation, alright, so if your pipe were to climb up or go down, alright, there would be pressure drop due to the elevation, alright, H1 minus H2 or H2 minus H1, okay, alright. The third one is a bit more confusing because we didn't see this before. There's an acceleration term. Alright? Previously, we said steady state in our thing and then there was no acceleration. Alright, so our Bernoulli equation, energy equation, there's no acceleration. In this case, even a steady state will have acceleration. Why? Because, let's say even we go back this one, alright, from a boiler tubes, liquid become gas. The density is not going to be the same, isn't it? So the density will be reducing, or the specific volume will be increasing. Right now. So when the specific volume increases, m dot is the same, area is the same. What happens to the velocity? Increase or decrease? Okay. Okay, m dot is equal to rho A V. So in the case of boiling, this one is decreasing as we go along the pipe. Alright, it's changing from liquid to gas. Alright, m dot is the same, area is the same, pipe the same. So the velocity is increasing. Correct or not? Alright, let's say boiling in the pipe. Alright, so in that case, there is an acceleration of the fluid. with distance. Right? At each location, in steady state, at each location, the velocity is fixed. But this location to a location downstream, then the velocity will increase in the case of boiling. Is that okay? Huh? Yes, no. Right? Here. Right? So, with multi-phase flow, in this changing phase, you can expect an acceleration or deceleration. The other thing is, if your multi-phase flow, you have bubbles in here, alright? If your pressure, as you go down here, your pressure goes down, alright? This is your pressure. As you go along, your pressure drops, alright? The liquid density is not going to change that much, alright? Normally, no. Okay? So the density of the liquid approximately constant. Alright? But the density of the gas, what's going to happen to the density of the gas? Gas normally PV equals to RT, or P on rho equals to RT. So, assuming that the temperature stays constant, as the pressure drops, what happens to the density? Density also must drop. Right? This side constant. So if this one go down, this one also goes down. So that the ratio will maintain the same. Alright? Or the specific volume increase. Okay? So if this one constant, okay, so if the pressure goes down, pressure drops, the specific volume increases. Alright? It expands up. Alright? So if the gas expands, what happens to the velocity? Also increases, isn't it? Alright, if the gas expands, means the density goes down, it expands. Alright, m dot the same, m dot equals rho AV, so rho the same, A the same, the velocity increase. Alright, so in multi-phase flow, there are three factors at play. Number one, gravity, alright, elevation. Number two, friction from the walls, the friction factor, which we'll talk about more. And number three, what's number three? Acceleration, right? So the acceleration, the dv dx, alright, is not zero. Okay, it could be accelerating or decelerating, depending on the gas expanding, and therefore we need to consider those three factors. Okay, as I said, my lecture on this part, I don't go through equation by equation. By all means, if you want to, you can. I'm just going through the overview, more subjective, qualitative description. Okay. Any questions so far? So I think here, okay, by all means, yeah, we got the little control volume, we got all the little forces acting on it, and then a lot of this and churn, and basically you got these three components. Alright, this is due to friction, forces in the pipe. This is due to change of momentum, acceleration, deceleration. This is change of elevation or static head. Alright, the rho GH term, alright, or H2 minus H1 in your energy equation. Okay? Is that agreeable, everybody? Yeah? Okay. So, yeah. Alright. Usually, the case of acceleration, usually zero is density is constant. So if there's a normally density constant if it's a liquid. If it's a liquid and a gas, but the pressure change very small, maybe few kPa, then we can close one eye and say constant. Then we can use that as well. But if the pressure change is big, 100 kPa, 50 kPa, what cannot change. The volume, the gas actually volume might double. Alright, there's a big change in pressure. So you cannot neglect. Alright? Okay, two-phase flow. This one done already. Done. Done already. I think I skip this one. This one looks painful. Okay. Basically, there are different models that you could use to predict pressure drop in a pipe with two-phase flow. Homogeneous model is only one of them. All right, suitable for more the middle regime, the churn, not the all the way gas flow and not the all the way liquid flow, but more in the middle. All right, we assume two phases can be treated as one phase. Assume some uniform velocity, of course, given section. Also known as friction factor model, assume the friction component of the pressure gradient can be tried as single friction factor. All right. Expect to work better when one phase is dispersed in the other. It means one phase is the dominant one. There's one continuous phase and one dispersed phase. Okay. So these are the average properties for the bar. The rho bar is rho G plus rho L. There's something wrong there, isn't it? Alright. Right? Finally, I think there's something wrong with the top one. How are we adding the two things? Alright? Anyway, we won't use rho bar anyway. The specific volume, alright, is averaged out using the W is the what W? Quality is it? Alright? So the mass fraction of the gas times the specific volume of the gas plus the mass fraction of the liquid, 1 minus W, times the volumetric specific volume of the liquid. I think there's something wrong with the top one. Doesn't look quite right. Okay, never mind. Ignore the top one. We use that one. Okay, again, in reality, the gas and liquid can be moving in different velocity, but we assume there's one uniform velocity. Alright, this is part of the homogeneous flow model in pipe. Alright, that's why I separate the two. Earlier this morning, the gas and liquid in bubble column, they're moving at different speeds. Alright, and we study that. But in this case, we assume there's one speed. Alright. Therefore, the total mass flow rate is the rho bar US. U is the velocity. Rho VA. So, rho bar, average density. I think up there wrong. Alright. Use the second equation. This one is the average velocity and area. Okay. Let's see. Alright. So the earlier one, basically we still have these three. This is due to friction. This is due to acceleration. There you see there's a dx. Alright. G is what? G is MOS, isn't it? G is the mass flux. Is that correct? Alright, G is the mass flux, dx, is the acceleration term. And rho G, sin theta is just rho G H. Right? Or rho G sin theta because this is dx. Right? So if not, this is just rho G or the vertical component of between the 2 points. So 1 over S area. Okay? dF dx is the friction component. Okay. So yeah, I think this one just relate back to shear stress on the wall. Right? Because here we also use the fanning friction factor. Okay. Yeah, so fanning friction factor. Equation a little bit different than the Darcy one. Okay. Okay. Acceleration component. The acceleration is due to two things. Alright, I told you just now I explained the gas. I explained both. Alright, the gas can expand or contract. Now the liquid density is about the same, but the gas can expand or contract depending on the pressure change. and that's incorporated in here. The second one, if there's a phase change, alright, liquid converting to vapor, that also causes a pressure, that also causes a density change, and that also causes an acceleration. Alright, so there's two components in here. Alright, you want to follow the math through. Okay. So acceleration component is like this. So notice dP dx also depends on the dP dx. Right? Because the change in the gas phase is related to the change in pressure. And this one, dLg is the dL minus Vg is like the HFG. Yeah? Right? This is dLg, dL minus Vg, the change in density multiplied by the change in quality. So if there's a quality change due to boiling or condensation, then that multiplied by this also causes an acceleration curve. Right? Okay so far? Alright. So, and gravity one, well, that's just gravity, no problem. Alright. So you put all this together, rearrange, alright, put the dP dx to the left, put everything to the right, you get this term here. Alright. Let's examine a bit more in detail. Okay. So this is due to friction. Alright, your fanning friction factor in there. This is due to phase change. That's why there's a dW dx. Alright, the W is changing. This is due to gravity. No problem. This one is due to the gas expanding. Vg on dP. Alright? G squared, W is the quality, and this one is the normally P on D equal so what's it? So normally PV equals to RT, so V equals to RT over P. dV on dP is equal to, what is the differentiate this with respect to P? 1 over P differentiate with respect to P is what? RT over P squared. Minus 2. Okay. No. Minus 1. Alright. Does that look right? Okay. So, if there's a change in pressure, and we assume ideal gas, alright, it's approximately like so. Okay. All right. Oh no, I gone too far. Okay. So this is the equation that we do use. We know every term in there. All right. G F fanning. F fanning. Okay. F fanning at the moment unknown. All right. We need to figure out what that is for this mixture. We'll do that next. G is M over S, isn't it? All right. B bar is. It's to do with the W1. All right. Let me copy this one. Copy. Can paste here. No. Asking too much here. Okay.